Hello students. In the last video, I showed you guys a clip on the inner functions of the eye and how the invention of the camera is actually based off of the inspiration of how our eyes work, where the camera, all cameras have a lens, right? And the lens directs the light inside of the camera and directs it to a focal point, and that focal point is typically going to be on the film. Okay, very much like the human eye, the focal point is directed towards the retina, where then our brain processes the information of what we see. So anyway, the purpose of this video, okay, is to perhaps come up with an equation that describes this lens. Okay, so what I have right now, okay, is a lens, okay, and this lens is directing all of the light towards a particular focal point. Okay, so the lens is directing all the light towards a focal point. Now, what has to be clear, and I made a mistake already. There is a rule, okay, that you guys have to be familiar with in order for us to be able to construct the equation of the lens, and that is how exactly is the light being bent. Okay, so the rule is this. Okay, the distance that the light travels, okay, within the lens. Okay, I'm going to call that distance there. I'm going to call this P. That distance that the light travels within the lens, well, that distance travel from the lens to the focal point, okay, also has to be the same distance. Okay, and it doesn't matter where you are on the lens, where you are within the lens, I should say. So let's say if it travels in here, okay, and then from there, the lens will refract and bend the light, and it'll bend it towards the focal point. Same thing over here. The light travels inside of the lens, and then it bends the light towards the focal point, and that distance, okay, everywhere here, everywhere along the that path, it's got to be the same. So this is D1, this is D2. D1 and D2 has to be the same everywhere. So the shortest path, okay, between that vertex, okay, to this vertical line, and there's a name for this guy right here. This is called a directrix. Okay, so the distance between the directrix to the focal to the vertex of the lens, and then from the lens, from the vertex of the lens to the focal point, this point over here being the focus, has to be the same everywhere. So again, D1 and D2, and D1 and D2, okay, and so on and so forth. All of these lengths, okay, have to be the same. All right, and as you can see here, the shortest lengths for D1 and D2 is a length of P. Now, for us to, and again, the purpose of this video is to somehow describe this situation, okay? Describe this lens. So how are we going to do that? Well, whenever we're trying to come up with an equation, okay, it is best to, have some things that we can sort of like work off of and model off of, right? So what I'm going to do is I'm actually going to place this, okay, on a coordinate grid on an XY axis. So this is Y and this is X. So therefore, all the points on this lens, okay, all these points, okay, I'm going to call X comma Y. All of those points, okay, are X comma Y. They are some point on the lens itself. And then this point over here, okay, this particular point right here, I'm going to call that point there H comma K, because it happens to be an apex. It's a vertex. The curve is culminating together at that point, right? So it's fitting to call that h comma k a vertex. All right. And if we're going to call that point there the vertex h comma k, and if you notice this line over here, right, that shortest path between the directrix to the vertex is a length of p, and the path from the vertex to the focus is also a length of p. Well, that line there is horizontal. And how do we describe, well, not how do we describe, but if that is a horizontal line, and I want to come up with a way to describe the vertical line that is our directrix, this guy right here, this vertical line is our directrix, okay? If I want to come up with a way to describe that vertical line, I will use the vertex and the length of p to describe that vertical line. Because the directrix is a vertical line in this case, the equation for that vertical line will be x equals something, right? Because the way in which we describe a vertical line is always going to be x equals something. So x equal to what? So because h comma k is further to the right than the directrix, to find that, to describe the equation of that vertical line, well, that's just h minus p then, right? Because this vertical line is going to be p units to the left of h comma k, so therefore the equation for the directrix is x equals to h minus p. All right, so I have a couple things going for me right now. I have the equation for the directrix, which is, you know, where the light enters the lens, right? So where the light enters the lens. I now also have I am also told, or you're also told, some of the laws that has to happen with the light that enters the lens. Okay, the path inside the lens, the path of the light inside the lens, and then from the path of the light from the lens to the focus. Okay, that has to be the same length. Okay, that's another fact. And there's one more thing. Okay, since I'm referencing everything from the vertex h comma k, the focus can then be described in a very similar manner as the directrix. The focus, okay, will be p units to the right of h comma k, and if that's the case, then it will be h plus p comma k. So that's my focus. Okay, that's the coordinate for the focus. Okay, so I have a lot of things going for me right now. Okay, but most important of all, okay, is the law that's governing what's happening with the light. We're going to capitalize on that right there, d1 equal to d2. All right, so having said this, okay, and again, our goal, one more time, just keep that in mind, our goal is to come up with an equation that describes the lens. Okay? So we are going to, again, use that fact that d1 is equal to d2. So if that's the case, well, let's just come up with the equation for d1, right? So the equation for d1, what exactly is the equation for d1? Well, the equation for d1 is a horizontal line, right? Because the light is traveling from the outside world through the directrix and hitting the lens, right? Hitting the other side of the lens. So d1 is a horizontal line there. I want to know what is the distance between the directrix and x. Well, in order for us to do that, it's just x minus h minus p. That's all it is. Okay? So this point right here, let's say, okay, has a coordinate of h minus p, comma, y, because it's on the same level as the point on the other side. It has the same y coordinates. This is a horizontal line. All right, I want to apply the same concept to finding d2. So d2, okay, d2 is a little different because D2 does not necessarily have to be a horizontal line. It could be a horizontal line, but it could also be a slanted line, in which case then I need to use really the distance formula to figure this out. So according to the distance formula, what I need to do then is, it's this giant square root, okay, where I take the difference of the x's, right? So it's going to be x minus h plus p, quantity squared, plus y minus k, quantity squared. That's the equation for D2. And I am going to box this information because this is going to be important. We are going to capitalize on this right now. All right? So because of the law of that the light traveling within the lens, that path, okay, the length of the path of the light within the lens, and then from the length of the path from the lens to the focal point has to be the same, we are going to use this information to try to come up with the equation now. So because D1 is equal to D2, I am able to then say I can equate these two equations together in this manner. So these two things will therefore be the same. All right, there's a lot of stuff happening in here. It looks really, really awkward and, well, just really messy. What we're going to do, okay, because we want to come up with an equation to describe this lens, I'm going to direct you at this because I've done this proof like a million times. What we're going to do is we're going to try to isolate x. We're going to try to isolate x, and there's a reason for this. I'm going to hold off on explaining what that reason is until the very end, just because, again, this is from my experience leading with this proof. We're going to try to isolate x first, and I'll explain why in a moment, okay? All right, so when we isolate x, okay, to isolate x, okay, notice that there's x's on both sides of the equation. I want to get those x's out of the parentheses and out of the square roots. So how are we going to do that? Well, first thing we're going to do is we're going to square both sides. So if we do that, we'll end up with x minus h minus p, quantity squared, is equal to this stuff that's inside of the radical and right now it doesn't look like it's any less simplified. What we're going to do is, again, our goal, one more time, is to isolate x, right? So what I'm going to do, I'm going to very strategically foil different pieces of this equation. I am not going to foil this piece right here because this term here involves y. I don't really care for y at the moment. All I want to do is just try to isolate x. So because of that, I am going to strategically not foil that, but instead foil everything else. And if you're wondering, like, oh boy, you have a trinomial that you want to square, and you're right, okay, it is kind of like nasty looking, but we're going to foil this using a little bit of structure. So this is actually, if you recall, right, a difference is this perfect square. This is a squared minus 2ab plus b squared, and then well, this is going to be important. We're going to capitalize on this. So this, the left-hand side will FOIL to become x squared minus 2 times x times h minus p plus h minus p quantity squared. Pause the video for a moment if to see if you can confirm your understanding. Okay, that is the natural transition. Okay, from that step to the last step here. We're going to apply very, very similarly to the other side. What we'll end up with is x squared minus 2 times x times h plus p, and then plus h plus p quantity squared. And don't forget that other plus y minus k, y minus k quantity squared there. So I'm at the stage right now, immediately you're going to see that there are things that we can cancel. I can cancel out the x squared and x squared. And if I distribute the negative 2x into h minus p and into h plus p on either side, you're going to see more terms cancel out. So let's do that. So my next step is, I'm going to distribute the negative 2x, so I'll end up with negative 2xh plus 2xp plus h minus p quantity squared is equal to negative 2xh minus 2xp plus h plus p quantity squared plus y minus k quantity squared. And again, more things will start to cancel. I noticed that I have negative 2xh on either side. And I can also try to combine the 2xp's. So what I am going to do is I'm going to subtract both sides by, I'm going to subtract both sides by 2xp's. I will then subtract over these terms on the right over to the left-hand side. Okay, so that's what I'm going to do in the next step. So what will that look like then? What I'll end up with is I'll end up with negative 4xp, and on the on the left-hand side, what I'll end up with is h minus p quantity squared minus h plus p quantity squared, and then minus y minus k quantity squared. And there's more simplification that we can do, okay, to further reduce this, because if I FOIL out h minus p and FOIL out h plus p, and because there's we're subtracting two of them there are going to be terms that we can eliminate. So that's exactly what I'm going to do next in my next step here. So I'm going to FOIL that out. So I have h squared minus 2hp plus p squared, and then subtracted by h squared plus 2hp plus p squared. I am strategically, again, not foiling out the y minus k, and that is equal to negative 4xp. And here you're going to notice that the h squares and h squares will cancel. The hp and, whoops, not hp, what am I saying? The p squared and p squares will cancel. However, these negative hp and minus 2hp there, they will combine, okay? So that's what I want to do next, is I am going to combine them together. I end up with negative 4hp minus y minus k quantity squared is equal to negative 4xp. My second to last step, what I'm going to do is I am going to divide both sides by negative 4p. And if I do that, I'll end up with x is equal to, I'm just going to do a little bit of rearranging here. If you notice, the negative 4 and p will cancel out. Remember, we have to divide negative 4p into every term here. So not only into this, but also into this guy right there, right? So we got to do it to both. So what I'll end up with is, I'll end up with 1/4 p, 1/4p times y minus k quantity squared plus h. And lastly, I'm just going to do a little bit of rearranging. This is 1/4p times y minus k quantity squared plus h. This, ladies and gentlemen, right, is the equation that's describing that lens. Okay, so I'm just going to move this over so everything's in one shot. Okay, so this is everything in its entirety, okay? So this equation here is describing that lens, and if you notice, doesn't this equation here that I have boxed in look somewhat familiar? It's actually the equation of a parabola. As it turns out, this is the equation of a parabola that's oriented sideways, okay? So I want to write that over here. So this is the equation. So x minus, I want to use a thicker one. So x equals 1/4 p, x y minus k quantity squared plus h. This is the equation of a parabola. Equation of a sideways parabola. This is the equation of a sideways parabola involving focus and directrix. So this is a new way for us to define the equation of a parabola. And there's actually a lot more that we can discuss, but I want to leave that for another video. Okay?